There is a star in the southern sky that burns with the light of more than 1 million suns. Not 1,000, not 10,000, not 100,000, more than 1 million. It sits in a neighboring galaxy, roughly 160,000 light-years from Earth. And yet it is so luminous that on a clear night, under perfect conditions, you can see the cloud of stars surrounding it with nothing more than your naked eye. That cloud is the Large Magellanic Cloud, a satellite galaxy orbiting our own Milky Way, and buried within it, like a furnace hidden inside a snowstorm, is a single point of light so powerful that it redefines what we think a star can be. Its name is Doradus, and for more than a century, it has confused, frightened, and fascinated astronomers in equal measure. When we think of stars, most of us imagine something like our Sun, a modest yellow sphere about 860,000 miles across, burning hydrogen in its core at a temperature of roughly 15 million degrees Celsius. Our Sun is respectable, it is stable, it has been shining for 4.6 billion years, and it will continue for another 5 billion or so before it swells into a red giant and eventually fades into a white dwarf. It is, by every reasonable standard, an ordinary star, and that is precisely what makes Doradus so disturbing, because Doradus is not ordinary. It is not even extraordinary in the way that a star twice the size of our Sun would be extraordinary. Doradus exists at a level of stellar power that challenges our understanding of physics itself. It occupies a place in the cosmos where the very fabric of a star begins to tear under the pressure of its own radiance. Imagine for a moment that our Sun is a single candle flame sitting on a table in a darkened room, a warm, steady light, enough to read by, enough to cast gentle shadows on the walls. Now imagine replacing that candle with something else. Not 10 candles, not 100, not even 1,000 candles lined up along the table. Imagine replacing that single flame with a bonfire stretching 30 feet into the air, roaring with heat, so bright that it hurts to look at, so powerful that the walls of the room begin to char and crack. That is the kind of difference we are talking about. Doradus does not simply outshine our Sun, it obliterates the comparison entirely. At its peak brightness, it radiates energy at a rate that would require more than 1 million copies of our Sun, fused together, burning simultaneously, to match one star. One single, seething, unstable object, pouring light and heat into the void at a rate that seems almost physically impossible. And it gets stranger, because Doradus does not shine steadily. It pulses, it fluctuates, it surges and subsides. Over periods of years and decades, its brightness changes dramatically, sometimes by a full magnitude or more. It swells and contracts, heats and cools, as though the star itself is breathing, caught in a slow, agonizing struggle between gravity pulling inward and radiation pushing outward. This is not a calm, predictable cycle, like the gentle pulsing of a Cepheid variable. Those well-behaved stars, whose rhythmic brightening and dimming helped us first measure the distances to other galaxies. This is something more chaotic, more violent, more uncertain. Doradus belongs to a rare and terrifying class of stars known as luminous blue variables, or LBVs. These are the most luminous, most massive, most unstable stars in the known universe, and they do not last long. Their lives are spectacular and brief, measured not in the billions of years that our Sun enjoys, but in the mere millions. And the luminous blue variable phase itself, the period of wild instability that Doradus is currently experiencing, may last only a few tens of thousands of years, a cosmic heartbeat, a flicker in the dark. By the end of tonight, you're going to understand what Doradus truly is, why it behaves the way it does, and what its existence tells us about the most extreme limits of stellar physics. You are going to learn why there is a maximum brightness that any star can achieve before it begins to tear itself apart, and why Doradus dances right along that edge, sometimes stepping over it, sometimes pulling back, locked in a precarious balance that cannot last. You are going to discover what happens when a star is so luminous that its own light exerts more force than gravity can contain, and why the answer to that question has implications not just for this one star, but for the evolution of galaxies, the formation of black holes, the creation of the heaviest elements in the periodic table, and the ultimate origin of the atoms in your own body. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. The story of Enceladus is the story of a star living on borrowed time. It is a story about the boundaries of nature, about what happens when matter and energy collide at scales so immense that the rules we take for granted begin to bend and break. It is a story that starts with a faint smudge of light in a telescope eyepiece, observed more than 150 years ago by astronomers who had no idea what they were looking at. And it is a story that, even now, with all of our modern instruments and computational models, is still being written. There are questions about Enceladus that remain unanswered. There are behaviors it exhibits that our best theories cannot fully explain. And there are fates that may await it, outcomes so violent and so consequential that their effects would be felt across an entire galaxy. Now, let's begin. To understand Enceladus, we first have to understand what stars are, how they work, and why some of them grow to become monsters while others live quiet, unremarkable lives that stretch across billions of years. And to do that, we need to start with the most basic force in the universe, the force that builds everything and eventually destroys everything: gravity. Every atom in the cosmos pulls on every other atom. This is Newton's law of universal gravitation, first described by Isaac Newton in 1687, and it is beautifully simple. Mass attracts mass. The more mass you have, the stronger the pull, and the closer two objects are to each other, the stronger the force between them. This is the force that holds you to the surface of the Earth. It is the force that keeps the moon in orbit around our planet. It is the force that binds the Earth to the sun, that holds the solar system together, that shaped entire galaxies out of diffuse clouds of gas in the early universe. Gravity is patient, it is relentless, and over long enough timescales it always wins. A star is born when a cloud of gas, mostly hydrogen with a small fraction of helium, begins to collapse under its own gravitational attraction. These clouds are enormous. A typical stellar nursery, a region of space where new stars are forming, can stretch across tens of light years. A single light year is roughly 5.88 trillion miles, so a stellar nursery can span hundreds of trillions of miles, a volume of space so vast that light itself takes years to cross it. Within these vast clouds, pockets of slightly denser gas attract surrounding material, pulling it inward. As the gas falls toward the center of the pocket, it compresses. As it compresses, it heats up. This is a basic law of thermodynamics. When you squeeze a gas, its temperature rises. And when the temperature and pressure at the center of this collapsing cloud reach a critical threshold, roughly 10 million degrees Celsius, something extraordinary happens. Hydrogen nuclei, which are simply individual protons, begin to smash together with enough energy to overcome their mutual electrical repulsion. They fuse. They combine to form helium, and in the process, a tiny fraction of their mass is converted into energy according to Einstein's famous equation. Energy equals mass times the speed of light squared. The speed of light is enormous. It is roughly 299,792 kilometers per second. And when you square that number, the result is staggering. Even a minuscule amount of mass, converted entirely into energy, releases a phenomenal quantity of light and heat. This is what powers every star in the universe. This is nuclear fusion. This is the fire at the heart of our sun. Our sun converts approximately 620 million metric tons of hydrogen into helium every single second. Every second. 620 million tons of matter transformed, with roughly 4.3 million tons of that mass vanishing entirely, converted into pure energy in the form of photons. These photons, born as gamma rays in the core, slowly work their way outward through the dense interior of the star, bouncing off atom after atom, gradually losing energy, until they finally escape from the surface as visible light, infrared radiation, and ultraviolet rays. It takes a photon roughly 170,000 years to travel from the core to the surface. 170,000 years of random bouncing through the dense plasma of the solar interior. A journey that covers, in actual distance, far more than the 93 million miles separating the Sun from the Earth. And then, once it reaches the surface, that same photon crosses the entire gulf between the Sun and the Earth in just 8 minutes and 20 seconds. The journey through the vacuum is almost instantaneous compared to the tortuous journey through the star itself. This gives us some sense of how dense and opaque the interior of even an ordinary star truly is. The Sun is massive. It contains roughly 330,000 times the mass of the Earth. Let us put that number in perspective. If you could place the Earth on one side of a cosmic scale and begin stacking copies of the Earth on the other side, you would need 330,000 Earths to balance the Sun. If you could hollow out the Sun and fill it with Earths, you could fit approximately 1.3 million of them inside, packed together like marbles in a jar. The Sun dominates our solar system utterly. It contains 99.86% of all the mass in the entire system. Every planet, every moon, every asteroid, every comet, every grain of dust, all of it together amounts to less than 0.2% of the Sun's bulk. Jupiter, the largest planet, massive enough to contain more than 1,300 Earths, still amounts to only about 1/1000th the mass of the Sun. The Sun is the solar system. Everything else is debris. And yet, by stellar standards, the Sun is small. It is average. It is a perfectly ordinary G-type main sequence star, sitting in the middle of the range of stellar masses, temperatures, and luminosities. It is the stellar equivalent of a sedan in a parking lot full of sedans. There is nothing wrong with it. There is nothing special about it. And compared to Enceladus, our Sun is almost invisible. The difference in scale between our Sun and Enceladus is comparable to the difference between a matchstick and a forest fire. They operate on the same basic principles. They both involve combustion, in the broadest sense. But the magnitude of energy involved is so different that comparing them requires us to abandon our everyday intuitions and think in terms that the human brain was never designed to handle. Let us build toward that comparison slowly, step by step, because the scale involved is genuinely difficult for the human mind to absorb. Our brains evolved to understand distances we could walk in a day, quantities we could count on our fingers, temperatures we could feel on our skin. The numbers we are about to encounter are so far beyond everyday experience that they become abstract, meaningless strings of syllables, unless we anchor them to something familiar. This is why scaled comparisons are so important. They do not make the numbers smaller, they make them real. Consider first the star Sirius, the brightest star in our night sky, a beacon in the constellation Canis Major that has guided sailors and fascinated observers for thousands of years. Ancient Egyptians built their calendar partly around the heliacal rising of Sirius, the moment each year when the star first becomes visible on the eastern horizon just before dawn. Sirius is roughly twice the mass of the Sun and about 25 times more luminous. That means if you replaced our Sun with Sirius at the center of the solar system, the Earth would receive 25 times more light and heat than it currently does. The oceans would boil. The atmosphere would be stripped away within a cosmically short time. Life as we know it would be impossible. 25 times the luminosity of the Sun is already catastrophic from our perspective. But 25 is a small number in the world of stellar astrophysics. It barely registers on the scale of what stars can achieve. Now consider Rigel, the bright blue-white star that marks the left foot of the constellation Orion, one of the most recognizable figures in the winter sky. Rigel sits roughly 860 light-years from Earth. It is approximately 21 times the mass of the Sun, a genuine heavyweight by stellar standards, and its luminosity is roughly 120,000 times greater than our Sun's. If our Sun were a single match flame flickering quietly on a table, Rigel would be a searchlight mounted on the roof of a skyscraper, throwing a beam visible from miles away. Rigel is a blue supergiant, a rare and powerful star nearing the end of its life. It has probably already exhausted the hydrogen fuel in its core, and is now burning helium or heavier elements in a series of ever shorter nuclear burning stages. It is impressive, it is extreme, and it is still nowhere close to Enceladus. Enceladus is estimated to carry somewhere between 25 and 100 times the mass of the Sun, depending on the measurement technique and the specific epoch of observation, because its properties change over time in ways that make precise measurements difficult. At its peak luminosity, Enceladus radiates at a rate of roughly 1 million times the luminosity of the Sun. Some estimates have placed this figure even higher. That number is so large that it defies intuition. So let us try several scaled comparisons to make it tangible. Imagine that our sun's total light output, all of its energy, every photon it produces, could be represented by a single grain of sand. One tiny, pale grain sitting in the palm of your hand. You can feel its weight, you can see its shape. It is real, it is comprehensible. Now imagine that you needed to represent the light output of Enceladus using grains of sand at the same scale. You would need 1 million grains. 1 million grains of sand would fill roughly a small cup, the kind you might use for a shot of espresso. Our sun is 1 grain. Enceladus fills a cup. 1 grain versus a cup. That is the difference between an ordinary star and a luminous blue variable at the upper extreme of stellar luminosity. Here is another way to feel the scale. Light from the sun takes about 8 minutes and 20 seconds to reach Earth, travelling at roughly 300,000 kilometers per second. That light warms our planet, drives our weather systems, powers photosynthesis, and sustains all life on Earth. Now imagine that same sun, with all its warmth and energy, were placed at the distance of Enceladus, roughly 160,000 light-years away. At that distance, the sun would be utterly invisible, not dim, not faint, invisible. No telescope currently in existence could pick it out as an individual star among the billions in the Large Magellanic Cloud. It would vanish into the general glow of the galaxy, indistinguishable from the background. But Enceladus, sitting at that exact same distance, 160,000 light-years from us, is not invisible. It is not even faint. It is one of the brightest individual stars identifiable in the entire Large Magellanic Cloud. From 160,000 light-years away, it registers clearly and unmistakably on photographic plates and modern electronic detectors. That is what 1 million solar luminosities means in practical terms. It means visibility across intergalactic distances. It means a single star shining brightly enough to be noticed from another galaxy. If you were to drive a car toward Enceladus at highway speed, say 100 kilometers per hour, and if you could somehow cross the vacuum of intergalactic space in an automobile, it would take you roughly 1.7 trillion years to arrive. 1.7 trillion years. The universe itself is only 13.8 billion years old. You would need to wait for the universe to live out its entire current lifespan, more than 120 times over, before you would arrive at Enceladus by car. That is the kind of distance we are talking about. And yet, the light from this star crosses that distance and reaches our instruments as a clear, measurable signal. That is the power of 1 million solar luminosities. The Large Magellanic Cloud itself deserves attention here, because it provides the cosmic neighborhood in which Enceladus resides, and because its proximity to the Milky Way is what makes detailed study of this extraordinary star possible. The LMC, as astronomers often abbreviate it, is a dwarf irregular galaxy, smaller and less structured than our own spiral-shaped Milky Way. It contains roughly 30 billion stars, compared to the Milky Way's estimated 200 to 400 billion. It orbits the Milky Way at a distance of about 160,000 light-years, making it one of the closest galaxies to our own. It is visible from the southern hemisphere as a faint, elongated smudge of light in the constellations Doradus and Mensa near the south celestial pole. Indigenous peoples of Australia, southern Africa, and South America knew about it for thousands of years before European contact. European astronomers became aware of it during the voyages of Ferdinand Magellan's expedition in 1519 through 1522, which is how it came to bear his name. The LMC has been a treasure trove for astronomers, because it is close enough for us to resolve individual stars, yet far enough that all the stars in it are at roughly the same distance from us. It provides a natural laboratory for studying stellar evolution. When you observe two stars in the LMC that have different apparent brightnesses, you know that the difference is real, not merely a matter of one being closer than the other. They are both effectively at the same distance. This makes the LMC invaluable for calibrating the cosmic distance scale, for studying how stars of different masses evolve, and for observing rare, extreme objects like Enceladus in extraordinary detail. Enceladus was catalogued in the late 19th century during systematic photographic surveys of the southern sky. The naming convention for variable stars assigns letters to each variable star discovered in a given constellation, starting with R, then S, T, and so on. S Doradus means the variable star S in the constellation Doradus. At the time of its cataloguing, astronomers knew only that it was bright and that its brightness changed over time. They had no understanding of what kind of star it was, how far away it truly was, or why it behaved so strangely. That understanding would take many decades to develop. In some respects, it is still developing today, with new observations from modern ground-based and space-based telescopes adding fresh complexity to an already challenging picture. What astronomers gradually came to realize, through patient observation spanning the better part of a century, was that S Doradus was not merely a variable star among many. It was a prototype. It defined an entire class of stellar behavior. The luminous blue variables, sometimes called S Doradus variables in older astronomical literature, are named after this star precisely because it was among the first of its kind to be systematically studied and characterized. These are stars of extraordinary mass and luminosity, typically carrying between 25 and several hundred solar masses, shining at hundreds of thousands to millions of times the sun's luminosity. They are blue, indicating extremely high surface temperatures, often between 12,000 and 30,000 Kelvin during their quiescent phases. And they are variable, sometimes dramatically so, shifting in brightness by 1 to 2 visual magnitudes over periods of months to decades, in patterns that are irregular, unpredictable, and sometimes violent. To grasp what a shift of 1 or 2 magnitudes means, we need to understand the magnitude system. This system has ancient roots, stretching back to the Greek astronomer Hipparchus in the 2nd century before the Common Era. Hipparchus ranked stars by their apparent brightness, calling the brightest stars 1st magnitude and the faintest visible stars 6th magnitude. Modern astronomy has formalized this system into a precise logarithmic scale. Each step of 1 magnitude corresponds to a brightness ratio of approximately 2.512. A difference of 5 magnitudes corresponds to a brightness ratio of exactly 100. So when we say S Doradus varies by 1 to 2 visual magnitudes, we are saying its apparent brightness can change by a factor of roughly 2.5 to 6.3. For a star already shining at 1,000,000 times the sun's luminosity, that factor of 6 represents hundreds of thousands of solar luminosities being redistributed. The question that S Doradus poses is deceptively simple. How can a star that massive and that luminous exist at all without destroying itself? Because there is a theoretical upper limit to how bright a star can be before it begins to tear itself apart. That limit is called the Eddington luminosity, named after the British astrophysicist Sir Arthur Stanley Eddington. And S Doradus appears to spend its entire life pressed against that limit, like a balloon inflated to the very edge of bursting. What scientists discovered about S Doradus and stars like it turned out to be far more unsettling than anyone expected when those first photographic plates were exposed in the cool night air of Southern Hemisphere observatories more than a century ago. And it is to that discovery that we now turn. Every star that has ever existed is a battlefield. From the moment of its birth to the moment of its death, a star is the site of an unceasing war between 2 fundamental forces of nature. On one side is gravity, the great assembler, pulling inward with patient, inexorable force, trying to collapse the star into the smallest, densest possible configuration. On the other side is the combined pressure of radiation and hot gas, pushing outward, generated by the nuclear fusion reactions raging in the star's core, a torrent of photons streaming outward, battering against atoms, pushing them away from the center. In a stable star like our Sun, these 2 forces exist in approximate balance. Gravity pulls in, pressure pushes out, neither wins. The star holds its shape, maintains its size and temperature, and shines with a steady, reliable luminosity for billions of years. This balance is called hydrostatic equilibrium, and it is the single most important concept in stellar astrophysics. It is the reason stars exist as coherent, long-lived objects at all, rather than as fleeting explosions of nuclear fire that flare and fade in an instant. But this balance has a dangerous dependency. It depends on mass. The more massive a star is, the stronger its gravitational pull at the core, and the stronger gravity pulls inward, the hotter and denser the core must become to generate enough outward pressure to resist the collapse. A more massive star burns hotter, it fuses hydrogen faster, it produces more energy per second, and all of that energy, streaming outward through the star's interior as photons, exerts pressure on the matter above it. Each photon, when it strikes an atom or an electron, delivers a tiny kick, a minuscule push in the outward direction. One photon does almost nothing. 100 photons do almost nothing. But when trillions upon trillions upon trillions of photons are streaming outward every second, each one delivering its tiny kick, the cumulative force becomes enormous. This is radiation pressure, and it is fundamentally different from the thermal gas pressure that supports low-mass stars like our Sun. In a low-mass star, the dominant source of outward support is thermal pressure. The atoms and ions in the star's interior are hot. They are moving rapidly. Their kinetic energy creates a pressure that resists gravitational compression, much as the air inside a balloon resists being squeezed. Radiation pressure exists in these stars, but it is relatively modest, contributing only a small fraction of the total support. In a star 10 times the mass of the Sun, radiation pressure becomes more important, contributing perhaps 10 to 20% of the total support. In a star 50 times the mass of the Sun, radiation pressure is the dominant force, responsible for the majority of the outward push that keeps the star from collapsing. And this is where things become dangerous. Because radiation pressure, unlike thermal gas pressure, has a very particular relationship with luminosity. The more luminous the star, the stronger the radiation pressure. And if the luminosity rises high enough, the radiation pressure at the star's surface will exceed the gravitational attraction. When that happens, the surface layers are no longer bound, they are blown away. The star begins to evaporate, shedding mass through the sheer force of its own light. This is where the Eddington limit enters the story, and where the crisis at the heart of Doradus becomes clear. Sir Arthur Stanley Eddington was born on December 28, 1882, in Kendal, a small town in the Lake District of northern England. He was a Quaker, a pacifist during the First World War, and one of the most brilliant minds of the early 20th century. His contributions to astrophysics were foundational. He was among the first to propose that stars are powered by nuclear fusion, at a time when most physicists believed that gravitational contraction was the primary energy source. In 1990, he led the famous solar eclipse expedition to the island of Principe off the west coast of Africa, where he observed the bending of starlight by the sun's gravity, providing the first experimental confirmation of Einstein's general theory of relativity. This result made Einstein a global celebrity and cemented Eddington's reputation as one of the leading physicists of his era. And in the early 1920s, Eddington turned his formidable intellect to the internal structure of stars, publishing a series of papers that would fundamentally reshape our understanding of how the most massive stars function and why they are inherently unstable. Eddington's key insight was this: in a very luminous star, the radiation pressure exerted by the outward flowing light approaches and eventually equals the inward gravitational force at the star's surface. When these two forces are exactly equal, the star's outer atmosphere is in a state of zero net force. It neither falls inward nor flows outward, it simply floats. But if the luminosity increases even slightly beyond this critical value, the radiation pressure exceeds gravity. The outer atmosphere is no longer gravitationally bound. Material begins to stream away from the star's surface, driven outward by the sheer force of light. The star begins to evaporate. The luminosity at which this critical balance occurs is the Eddington luminosity, sometimes called the Eddington limit. Its precise value depends on two things: the star's mass and the opacity of its atmosphere, meaning how strongly the atmospheric material interacts with the passing radiation. Higher opacity means more interaction, more momentum transfer from photons to matter, and therefore a lower Eddington luminosity. For a star composed primarily of ionized hydrogen, with electron scattering as the dominant source of opacity, the Eddington luminosity scales linearly with mass. A star of 10 solar masses has an Eddington luminosity of roughly 320,000 solar luminosities. A star of 50 solar masses has an Eddington luminosity of roughly 1.6 million solar luminosities. A star of 100 solar masses has an Eddington luminosity of roughly 3.2 million solar luminosities. These are approximate figures, and they change significantly when you account for the more complex opacity of real stellar atmospheres, where elements heavier than hydrogen contribute additional absorption, but they provide the essential scale. Doradus, with its luminosity of roughly 1 million solar luminosities or more, and its mass of somewhere between 25 and perhaps 100 solar masses, is living at, or very near its own Eddington limit. It is a star whose outward radiation pressure nearly matches its own gravity, and this is not a comfortable position. It is, in fact, one of the most perilous states of existence possible for any object in the universe. Consider a simple analogy. Imagine a ball balanced on the peak of a very narrow hill. In perfect balance, the ball sits still, but the equilibrium is unstable. The slightest breeze, the slightest vibration in the ground, the slightest nudge in any direction, and the ball begins to roll. It cannot easily return to the peak. It falls away. Doradus is like that ball. Its balance between gravity and radiation is precarious, and any small perturbation, a fluctuation in the fusion rate in the core, a shift in the opacity of the outer layers, a change in the chemical composition at the surface due to convective mixing can tip the balance and send the star into an eruptive crisis. During these eruptions, the star's outer atmosphere responds in dramatic fashion. Material begins to flow outward, driven by radiation pressure that momentarily exceeds gravitational attraction. The atmosphere expands, sometimes enormously, reaching dimensions many times larger than the star's quiescent size. As it expands, it cools because the same amount of energy is now spread over a vastly larger surface area. The star's surface temperature drops from perhaps 25,000 Kelvin to 10,000 or even 8,000 Kelvin. Its color shifts from hot blue-white to cooler yellow or even reddish tones. And paradoxically, even though the star's total energy output, its bolometric luminosity summed over all wavelengths, may remain roughly constant during these episodes, it appears to brighten in visible light. This is because the peak of its radiation shifts from the ultraviolet, which our eyes and many ground-based detectors are insensitive to, into the visible part of the spectrum. The star is not actually producing more total energy. It is simply emitting more of that energy in wavelengths that we can detect. This is a subtle but important distinction. It is a trick of wavelengths, a redistribution of photons, across the electromagnetic spectrum, not a change in the total power output of the star. The mass loss associated with these eruptions is staggering by the standards of ordinary stellar physics. Our Sun loses mass through its solar wind, the steady stream of charged particles that flows outward from its corona into interplanetary space. This mass loss is extremely modest. The Sun sheds roughly 2 to 3 times 10 to the negative 14 solar masses per year. That tiny number means the Sun loses about 1 Earth mass every 150 million years. It is negligible. The Sun will exhaust its hydrogen fuel billions of years before its solar wind makes any meaningful dent in its total mass. Doradus is a very different story. During its eruptive phases, Doradus loses mass at a rate estimated between 10 to the negative 5 and 10 to the negative 4 solar masses per year. Let us translate that into more concrete terms. 1/10,000th of a solar mass is equivalent to roughly 33 Earth masses. Doradus during a major eruption can eject the equivalent of more than 30 Earth's material into space every single year. Not over a century, not over a millennium, every year. And some eruptions can last for decades. Over the course of a single multi-decade eruption, Doradus can shed hundreds of Earth masses of material. This material does not simply vanish. It expands outward into the surrounding space, forming a nebula, a slowly growing shell of gas and dust, enriched with the products of nuclear burning in the star's core. If you could weigh the nebula around a mature LBV, it would contain more mass than many entire star systems. And it gets worse, because the mass loss is not smooth, not steady, not predictable. It comes in pulses and surges, driven by instabilities that are still only partially understood. Sometimes the star enters a relatively quiescent phase, and the mass loss rate drops. The atmosphere contracts somewhat. The surface temperature rises. The star appears hotter and bluer. Then, without obvious warning, another eruption begins. The atmosphere inflates again. The temperature drops. Mass streams outward. The nebula around the star grows thicker and more complex. Each cycle strips the star of more of its substance, peeling away layers like the skin of an onion, exposing progressively hotter and denser material from deeper inside the star. And each cycle brings the star one step closer to the end of its life. Among the most informative comparisons for understanding Enceladus is the case of Eta Carinae, another luminous blue variable located in our own Milky Way galaxy, roughly 7,500 light-years from Earth, in the Carina Nebula. Eta Carinae is in many ways Enceladus's more dramatic cousin. In the 1840s, Eta Carinae underwent a colossal eruption known as the Great Eruption, during which it briefly became the second brightest star in the entire night sky, surpassed only by Sirius. This is remarkable because Sirius is only 8.6 light-years away, while Eta Carinae is nearly 1,000 times farther. For Eta Carinae to rival Sirius in apparent brightness from such a vastly greater distance, its true luminosity during the eruption must have been staggering. Estimates suggest it may have briefly reached 5 million solar luminosities or more, and some calculations place the peak as high as 50 million solar luminosities during the most intense phases. During the Great Eruption, Eta Carinae ejected roughly 10 to 40 solar masses of material into space, that is 10 to 40 times the entire mass of our Sun, flung outward in a single eruptive episode lasting roughly 2 decades. This ejected material formed the spectacular Homunculus Nebula, a bipolar structure of gas and dust that surrounds Eta Carinae today and that modern telescopes have imaged in exquisite detail. The homunculus consists of 2 lobes, expanding outward in opposite directions from the central star at speeds of roughly 650 kilometers per second. Its total mass is estimated at between 10 and 40 solar masses, consistent with the amount of material believed to have been ejected during the Great Eruption. The Great Eruption of Eta Carinae was not a supernova. The star survived, but the event was so energetic that for many years, astronomers debated whether it was truly an eruption or some entirely new category of astrophysical event, something between a nova and a supernova. The energy released, estimated at roughly 10 to the 49th to 10 to the 50th ergs, was comparable to a weak supernova, and yet the star persisted. This kind of event, sometimes called a supernova imposter, occurs when a massive star expels enormous mass in a non-terminal explosion, mimicking the brightness of a supernova without destroying the star. The mechanisms behind such events remain a topic of active research and intense debate. The instabilities that drive LBV eruptions are believed to arise from several interacting physical mechanisms. Chief among them is the iron opacity bump, a phenomenon that occurs deep inside massive stellar envelopes. At temperatures of roughly 150,000 to 200,000 Kelvin, iron atoms exist in a partially ionized state that makes them extraordinarily efficient at absorbing photons. This creates a zone of dramatically enhanced opacity inside the star, a layer where the passage of radiation is impeded far more than in the regions above or below. Photons trying to escape outward through this layer are absorbed and re-emitted many times, building up radiation pressure within the layer itself. When this trapped radiation pressure becomes too great, the layer surges outward, inflating the star's outer envelope and triggering the kind of atmospheric expansion we observe as an LBV eruption. The iron opacity bump is not a speculative hypothesis. It is a measured property of hot, dense matter, calculated from quantum mechanical models and confirmed by laboratory experiments. Its role in stellar instability is a direct and unavoidable consequence of atomic physics. A second mechanism is the intrinsic instability of any structure that exists near its Eddington limit. When a star's luminosity is close to the maximum that its gravity can contain, even small perturbations can cascade into large-scale disruptions. A 1% fluctuation in luminosity, or a slight change in the opacity of the outer layers, can tip the balance from stable equilibrium to runaway expansion. The star sheds material, temporarily dropping below the Eddington limit. But as it continues to evolve, burning heavier fuels and adjusting its internal structure, its luminosity creeps back up toward the limit, setting the stage for the next eruption. It is a cycle of approach, exceed, retreat, and approach again, a repetitive pattern of instability that can persist for thousands of years. Rotation adds another layer of complexity. Massive stars often rotate rapidly, and rotation modifies the effective gravity at the star's surface. At the equator, centrifugal force partially counteracts gravitational pull, reducing the effective gravity and lowering the effective Eddington limit in the equatorial plane. A rotating star can exceed its Eddington limit at the equator while remaining safely below it at the poles, leading to preferential mass loss from the equatorial regions. This may explain the bipolar shapes of some LBV nebulae, including Eta Carinae's homunculus. But here's what makes this truly terrifying. Enceladus is not evolving toward stability, it is evolving toward catastrophe. The luminous blue variable phase is not a permanent state. It is a transitional period in the life of the most massive stars, a brief interval of instability between the main sequence and the star's ultimate fate. That fate is either a transition to a Wolf-Rayet star, a bare stellar core that has been stripped of its hydrogen envelope, or a direct supernova explosion from the LBV state itself. Either path ends in the same place, the death of the star through the catastrophic collapse of its core, followed by either a supernova explosion or the formation of a black hole. And that end may come far sooner than we are accustomed to thinking about when we discuss astronomical timescales. The study of Enceladus and its kin has been one of the great ongoing challenges of modern stellar astrophysics. These stars are rare, crossed the entire Large Magellanic Cloud. With its 30 billion stars, only a handful of confirmed luminous blue variables have been identified. In our own Milky Way, which contains 10 times as many stars, the number is not much larger, perhaps a dozen or so well-characterized LBVs, along with a handful of candidates still being evaluated. These are not common objects. They represent the most extreme end of the stellar mass distribution, the very tip of the tail. Finding them is difficult. Studying them is harder. And understanding them has required contributions from multiple generations of astronomers using techniques that span the full range of observational astrophysics. Let us trace through the most important lines of investigation, the sustained attempts to understand what Enceladus is and why it behaves the way it does. Each approach has yielded genuine insights, and each has encountered serious limitations that have pushed the inquiry in new directions. The first sustained attempt to understand Enceladus came from the analysis of its light curve, the historical record of its brightness over time. Beginning in the late 1800s, astronomers at observatory in Cape Town, Melbourne, and later in Chile began recording the brightness of Enceladus on photographic plates, comparing it night after night, month after month, year after year, to reference stars of known and stable brightness. This was laborious work. Early photographic emulsions were inconsistent, atmospheric conditions varied unpredictably, and measuring the brightness of a star by comparing the sizes and densities of photographic dots on a glass plate was an art as much as a science, subject to systematic errors that could take years to identify and correct. But over the decades, a coherent picture emerged. The light curve of Enceladus showed variability on multiple distinct timescales. There were slow, sweeping undulations spanning decades, where the star would gradually brighten, hold near a peak for several years, and then slowly fade over a comparable period. Superimposed on these were shorter-term fluctuations on timescales of months to a few years, smaller in amplitude but clearly present. And occasionally there were sharper, more dramatic changes that did not fit neatly into either pattern, sudden jumps or drops in brightness that appeared over timescales of weeks or even days. By the middle of the 20th century, light curves stretching back more than half a century had been compiled from multiple observatories, and the complexity of Enceladus's behavior was becoming undeniable. The natural first hypothesis was that Enceladus was a pulsating star, similar to the well-studied Cepheid variables, but scaled up to higher masses and luminosities. Cepheid variables are stars that expand and contract in a regular, repeating rhythm, driven by a well-understood opacity mechanism called the kappa mechanism. In a Cepheid, a layer of partially ionized helium in the star's envelope acts as a thermostat. When the star contracts and the layer heats up, the helium becomes more ionized and more opaque, trapping more radiation and building up pressure that causes the star to expand. When the star expands and the layer cools, the helium recombines, becomes more transparent and allows radiation to escape, reducing the pressure and causing the star to contract again. This produces a beautifully regular oscillation with a period that is tightly correlated with the star's luminosity. It was Henrietta Swan Leavitt who first identified this period luminosity relationship in 1912 using Cepheids in the Small Magellanic Cloud, and it became one of the most important tools for measuring cosmic distances. But when theorists applied standard pulsation models to Enceladus and other LBVs, the results were wholly unsatisfactory. The predicted pulsation periods were far too short. Standard radial pulsation models for a star of 50 to 100 solar masses, using the Kappa mechanism or any of its known variants, produced periods of days to perhaps a few weeks. The observed variability of Enceladus, with its decade-long timescales and irregular patterns, was completely inconsistent with these predictions. The predicted pulsation amplitudes were also wrong, too small by at least an order of magnitude, and the shape of the light curve was wrong. Classical pulsators produce smooth, repeating waveforms, while Enceladus's light curve was irregular, asymmetric, and different from cycle to cycle, as though each oscillation followed its own rules. Classical pulsation theory, so successful at explaining Cepheids and RR Lyrae stars, simply could not account for the behavior of luminous blue variables. Something fundamentally different was at work. The second major approach centered on the concept of radiation-driven winds and the Eddington limit. In the 1970s and 80s, as the theory of radiation-driven stellar winds matured through the pioneering work of Castor, Abbott and Klein in 1975, astronomers began to apply these ideas to the most luminous stars. The Castor-Abbott-Klein theory, often abbreviated as CK theory, established a rigorous framework for understanding how radiation pressure on spectral absorption lines, the specific wavelengths at which individual elements absorb photons, can drive powerful outflows from hot stars. For ordinary hot stars, the cake theory predicted wind mass loss rates and velocities that matched observations very well. It was a triumph of theoretical astrophysics. For stars near the Eddington limit, however, the situation was more complicated. Theoretical work in the 1980s and 90s by researchers including Henny Lamers, Rolf Kadritsky, Jorik Vink, and others explored what happens when the underlying star is very close to its maximum allowed luminosity. They found that as a star approaches the Eddington limit, the wind mass loss rate can increase dramatically, by orders of magnitude, producing a phenomenon sometimes called a super Eddington wind or an optically thick wind. In this regime, the wind is no longer a thin, transparent stream of particles flowing off the star's surface. Instead, it becomes thick, dense, and opaque. The wind itself becomes a kind of extended atmosphere, a bloated pseudo-photosphere that can expand to many times the star's actual physical radius. This pseudo-photosphere is cooler than the star's true surface, and it radiates at a lower effective temperature, explaining the observed cooling and reddening of LBVs during their eruptive phases. This Eddington wind model was a genuine breakthrough. It correctly predicted several key features of LBV behavior. It explained why the bolometric luminosity remains roughly constant during Enceladus phases, while the visual brightness increases. It explained the temperature decrease and the color change. It predicted the existence of dense, slow-moving winds during eruptions, consistent with spectroscopic observations showing low outflow velocities of roughly 100 to 300 km per second during LBV eruptions, compared to the much faster winds of 1,000 to 3,000 km per second observed during quiescent phases. But the problem was causation. The model described what happens when a star is near the Eddington limit. It did not explain what pushes the star to the limit in the first place, or what triggers the transitions between quiescence and eruption. It was a model of consequences, not causes. Saying that Enceladus erupts because it approaches the Eddington limit is like saying a dam breaks because the water level exceeds its capacity. True, but incomplete without understanding what caused the water level to rise. The third approach went deeper into the interior of the star. In the 2000s and 2010s, advances in computational power and numerical methods allowed astrophysicists to construct detailed models of massive stellar interiors, including the effects of radiation transport, convection, and opacity. These models revealed a fascinating and troubling picture of conditions deep inside stars like S Doradus. The ion opacity bump turned out to be even more important than earlier work had suggested. Detailed opacity calculations using databases, like the OPAL tables from Lawrence Livermore National Laboratory and the OP tables from the International Opacity Project, showed that iron contributes a dramatic peak in opacity at temperatures around 150,000 to 200,000 Kelvin. In massive stars, this temperature corresponds to a layer within the stellar envelope above the core but below the visible surface. In this layer, the radiation pressure can locally exceed the gravitational attraction, even if the star's total luminosity is below the classical Eddington limit calculated at the surface. This creates what is called a supra-Eddington layer, a zone inside the star where the radiation field is literally too intense for gravity to hold the material in place. The math is striking. In the ion opacity zone of a star with a luminosity approaching 1 million solar luminosities, the ratio of radiation pressure to gas pressure can exceed 100 to 1. The radiation utterly dominates the mechanical balance. The gas is nearly irrelevant. In this regime, the envelope structure becomes inherently unstable. Strange convective motions develop, driven not by the familiar mechanism of hot gas rising and cool gas sinking, but by radiation energy trapped in an opaque layer, building up until it erupts outward. Numerical simulations by Matteo Cantiello, Yanfei Jiang, Lars Bildston, and others have shown that these radiation-dominated convective zones can produce dramatic density fluctuations, clumpy structures in the stellar envelope, and even episodic mass ejection events. These simulations represent some of the most computationally demanding calculations in modern astrophysics, requiring millions of processor hours on supercomputers to model even a small fraction of the stellar envelope in 3 dimensions. Despite this impressive computational effort, the third approach has significant limitations. Most published models are still restricted to 1 or 2 spatial dimensions, and the results depend sensitively on assumptions about boundary conditions, mixing prescriptions, and the treatment of convection that are difficult to validate against observations. Moreover, while these models can produce episodic instability and mass loss, they have difficulty reproducing the most extreme LBV events, particularly giant eruptions like the one Eta Carinae experienced, which seem to require energy deposition from deeper layers than the ion opacity zone. The fourth approach looked outward rather than inward, investigating whether S Doradus's behavior might be triggered or modulated by a binary companion star. This is a well-motivated hypothesis. Extensive surveys have consistently shown that the majority of massive stars, roughly 70% or more of O-type stars, exist in gravitationally bound binary or multiple star systems. The interactions between stars in a closed binary can be dramatic. Tidal forces can distort both stars. Mass transfer can occur when one star swells to overflow its Roche lobe, the gravitational boundary within which material is bound to that star rather than its companion. And in systems with eccentric orbits, the periodic close approaches at periastron can gravitationally perturb the outer atmosphere of one or both stars, potentially triggering instabilities and enhanced mass loss. The binary hypothesis gained significant credibility when detailed observations confirmed that Eta Carinae is a binary system. Its companion star orbits with a period of roughly 5.54 years in a highly eccentric orbit. At closest approach, the 2 stars pass within roughly 1.5 astronomical units of each other, close enough for intense gravitational and radiative interactions. Some researchers proposed that the great eruption of the 1840s was triggered, or at least significantly amplified, by a particularly energetic binary interaction, perhaps involving a collision between the 2 stars' winds, or even a brief episode of mass transfer. For S Doradus, the evidence for a binary companion is far less clear. Decades of spectroscopic monitoring have not revealed the kind of periodic radial velocity variations that would clearly indicate orbital motion around a companion. But this absence of evidence is not conclusive evidence of absence. the star's own spectroscopic variability, with its shifting emission lines, changing wind profiles, and fluctuating atmospheric conditions, creates a noisy background against which the subtle signature of a companion could easily be hidden. Enceladus might have a companion that is too faint, too distant, or too deeply embedded in the primary star's variable spectroscopic signal to be detected with current instruments, or it might truly be a single star. The question remains genuinely open. The fifth and most provocative approach challenges the assumption that LBV eruptions are driven primarily by processes in the stellar envelope. A growing body of theoretical work, championed by Nathan Smith at the University of Arizona and others, suggests that the most energetic eruptions may be powered by explosive energy release deep inside the star, in the nuclear burning shells that surround the core in evolved massive stars. In the final evolutionary stages of a massive star, multiple shells of nuclear burning surround a growing core. These shells burn different elements at different rates, and the transitions between burning stages can be violent. Shell flashes, brief but intense surges of nuclear energy release, can occur when a burning shell reignites after quiescence, or when fresh fuel is mixed into a hot burning zone by convective overshooting. These flashes can deposit enormous quantities of energy into the stellar envelope on very short timescales, far more energy than the envelope can radiate away. The excess energy must be released mechanically through an explosive expansion that drives material outward at high velocity. Smith and collaborators have argued that this deep interior mechanism is necessary to explain the energetics of the most extreme LBV events. The total energy released during Eta Carinae's Great Eruption, roughly 10 to the 49 to 10 to the 50th ergs, is difficult to account for through radiation-driven wind models alone. The kinetic energy of the ejected homunculus nebula requires a powerful, impulsive energy source, something more like a deep interior explosion than a gradual increase in radiative driving. This hypothesis blurs the boundary between LBV eruptions and genuine supernovae, raising the question of what exactly separates a star that ejects most of its envelope and survives from a star that ejects its envelope and dies. For Enceladus, no eruption as extreme as Eta Carinae's Great Eruption has been observed in the modern era. The variability we have documented is the more modest Enceladus phases, with brightness variations of 1 to 2 magnitudes and enhanced but not catastrophic mass loss. But this does not mean that Enceladus is incapable of a giant eruption. We have been watching it for roughly 140 years. The LBV phase may last 30,000 years or more. We may be seeing only a tiny, unrepresentative fragment of Enceladus's full eruptive history. A giant eruption may have occurred thousands of years ago, or it may occur thousands of years from now, or it may occur next decade. We simply do not know. There is also a sixth consideration that weaves through all of the approaches discussed above, and that is the role of metallicity. Metallicity, in astronomical usage, refers to the abundance of elements heavier than helium in a star's composition. The Large Magellanic Cloud has a lower metallicity than the Milky Way, roughly 1/2 to 1/3 the solar value. This means that stars in the LMC contain fewer iron atoms, fewer carbon and oxygen atoms relative to their total hydrogen and helium content. Since metals drive opacity and power stellar winds, lower metallicity affects nearly every aspect of a massive star's behavior: its wind mass loss rate, the strength of its iron opacity bump, the structure of its envelope, and its evolutionary trajectory from the main sequence to the grave. Enceladus, as an LBV in this lower metallicity environment, may behave differently from its counterparts in the metal-richer Milky Way, losing mass more slowly, retaining its hydrogen envelope longer, and following a somewhat different evolutionary path toward its ultimate fate. Each of these approaches has contributed real knowledge. None has been sufficient on its own. The current understanding of Enceladus and the luminous blue variables as a class is that their behavior results from the complex, nonlinear interaction of multiple physical mechanisms operating simultaneously at different depths and on different timescales within the star. The iron opacity bump may drive the quasi-periodic Enceladus phases. Deep interior instabilities may drive the rare, catastrophic giant eruptions. Binary interactions may modulate both. Metallicity sets the background conditions, And the Eddington limit provides the underlying context, the ever-present ceiling that makes all of these processes possible and consequential. Something is wrong with our assumptions whenever we try to reduce S. Doradus to a simple story with a single explanation. The star resists simplification. It demands a multifaceted understanding, a recognition that the most extreme objects in the universe are also the most complex. And perhaps that should not surprise us. Complexity tends to emerge at boundaries, at transitions, at the edges where one regime gives way to another. Yes, Doradus exists at the boundary between star and dispersing cloud, between gravitationally bound object and radiation-driven outflow. It is a boundary object. And boundary objects are always the hardest to understand and the most rewarding to study. Now we come to the part of this story that transcends astrophysics and touches on something more fundamental, because S. Doradus is not merely an interesting astronomical object. It is not merely a puzzle for theorists and observers to worry about. It is a window into the processes that created everything you see around you, everything you are made of, everything that makes your existence possible. And the view through that window is both magnificent and deeply unsettling. Here is the core truth that makes stars like S. Doradus so profoundly important. The universe, as it emerged from the Big Bang, roughly 13.8 billion years ago, was almost entirely composed of two elements, hydrogen and helium, in a ratio of roughly 75% to 25% by mass. There were trace amounts of lithium and beryllium produced during the first few minutes of cosmic history, when the temperature and density of the expanding fireball were briefly high enough to sustain nuclear reactions. But essentially nothing else. No carbon, no oxygen, no nitrogen, no iron, no silicon, no calcium, no phosphorus. None of the elements that make up the Earth, the oceans, the atmosphere, or the molecules of life. The early universe was chemically barren, a vast cooling sea of the two simplest atoms, stretching in every direction, with no planets, no rocks, no water, no chemistry of any complexity whatsoever. This is not a minor detail. This is one of the most consequential facts in all of science. Every element heavier than helium that exists today was created inside a star, every single one. The carbon in your cells, the oxygen in the air you breathe, the calcium in your bones, the iron in your blood, the nitrogen in your DNA, the phosphorus in your ATP, the sulfur in your proteins, all of it was forged in the nuclear fires at the centers of stars. Not stars like our Sun, which is a modest contributor to the cosmic inventory of heavy elements and will shed only its outer envelope during its eventual death as a red giant and white dwarf, leaving behind elements no heavier than carbon and oxygen. The truly heavy elements, the full palette of the periodic table, the elements that make rocky planets possible, that make water possible, that make organic chemistry possible, that make life possible, were produced overwhelmingly by the most massive stars in the universe. Stars like S. Doradus. This process is called stellar nucleosynthesis, and it is the fundamental engine of cosmic chemical evolution. It operates through a series of nuclear burning stages that occur sequentially in the cores of massive stars, each stage producing progressively heavier elements, and each stage running faster than the last, in a cascade that accelerates relentlessly toward the final catastrophe. Consider a star of roughly 25 solar masses, a reasonable estimate for S. Doradus in its earlier life, before it had shed so much of its original mass through its powerful winds and eruptions. Such a star begins its nuclear life by fusing hydrogen into helium in its core. This is the same basic reaction that powers our Sun, converting 4 hydrogen nuclei, 4 protons, into 1 helium nucleus, 2 protons and 2 neutrons, releasing energy in accordance with Einstein's famous equation relating energy to mass. The mass of the resulting helium nucleus is slightly less than the combined mass of the 4 original protons. That small deficit, roughly 0.7% of the original mass, is converted entirely into energy. It does not sound like much, 0.7%, but when you multiply it by the enormous quantities of hydrogen being processed in the core of a massive star, hundreds of millions of metric tons per second, the resulting energy output is staggering. In a massive star, however, the dominant pathway for hydrogen burning is not the proton-proton chain that powers our Sun. Instead, it is the carbon and nitrogen-oxygen cycle, or CNO cycle. In this process, pre-existing carbon, nitrogen, and oxygen nuclei act as catalysts, facilitating the step-by-step conversion of hydrogen into helium through a cyclic series of proton captures and beta decays. The CNO cycle is extraordinarily temperature sensitive. Its rate increases as roughly the 16th power of temperature, meaning that a modest increase in core temperature produces an enormous increase in energy generation. This extreme temperature sensitivity concentrates the energy production into the very center of the star, creating a steep temperature gradient that drives convective mixing throughout the core. This convective core is a churning, turbulent region where matter is continuously circulated from the center to the edge and back again, keeping the composition uniform and ensuring that fresh hydrogen fuel is always available for burning. A star of 25 solar masses will burn hydrogen in its core for approximately 7 million years. This is a long time by human standards, far longer than the entire span of recorded human civilization, but it is extremely brief by stellar standards. Our Sun, with its lower mass and more frugal energy budget, will burn hydrogen for roughly 10 billion years, more than 1,000 times longer. The massive star lives fast and dies young because it is so much more luminous, so much more profligate with its nuclear fuel. It has far more fuel than the Sun, roughly 25 times as much, but it burns it at more than 10,000 times the rate. The result is a drastically shortened lifespan. After the hydrogen is exhausted in the core, the nuclear fires die down. Without the outward pressure of energy generation to support the core against the inward pull of gravity, the core contracts. As it contracts, it heats up, squeezed by the immense weight of the overlying stellar material. The temperature rises from roughly 40 million Kelvin to over 100 million Kelvin, and at this point a new nuclear fuel ignites. Helium nuclei, which cannot fuse at lower temperatures because of the intense electromagnetic repulsion between their double-charged nuclei, begin to combine. 3 helium nuclei fuse to form a single carbon nucleus through the famous triple alpha process, named for the alpha particles, which is the traditional name for helium nuclei. Some of this carbon then captures an additional helium nucleus to form oxygen. These two reactions, 3 alpha to carbon and carbon plus alpha to oxygen, are the primary products of helium burning, and the precise ratio of carbon to oxygen produced during this stage has profound consequences for the subsequent evolution of the star and the chemical composition of its eventual remnant. Helium burning lasts roughly 700,000 years. During this phase and the stages that follow, the star develops an increasingly complex internal architecture. As each fuel is exhausted in the core and burning shifts to the next heavier element, the previous fuel continues to burn in a shell surrounding the core. The result is a layered structure, often described as an onion shell model, in which concentric shells of different nuclear burning surround a growing, increasingly dense core. The outermost shell, farthest from the center, burns hydrogen into helium. Inside that, a shell burns helium into carbon and oxygen. Inside that, carbon burns to neon and magnesium, and so on, each shell burning a progressively heavier fuel at progressively higher temperatures, until the innermost shell surrounds the iron core itself. This onion shell structure is one of the most remarkable architectural achievements in all of nature. A single star, a single gravitationally bound sphere of plasma, simultaneously hosting half a dozen different nuclear reactions at half a dozen different temperatures and densities, each reaction occurring in a distinct spatial zone, each zone feeding energy outward and ash inward, all of them coupled together by the flow of energy and matter through the intervening layers. The temperatures span a range from roughly 10 million Kelvin in the outermost hydrogen-burning shell to over 3 billion Kelvin in the innermost silicon-burning core, a factor of more than 300. The densities range from a few grams per cubic centimeter in the outer shells to over 10 million grams per cubic centimeter in the core, a factor of millions. And each shell is in a state of dynamic balance, adjusting its burning rate in response to changes in the pressure and temperature of the material above and below it, in a system of coupled feedbacks that is far too complex to solve analytically and taxes even the most powerful numerical simulations. The boundaries between these shells are not smooth, well-defined surfaces. They are turbulent, convective interfaces, where mixing can occur, dredging material from one burning zone into another, and potentially altering the nuclear products. Convective overshooting, the tendency of rising or sinking parcels of material to overshoot the nominal boundary of a convective zone due to their momentum, can transport fresh fuel into a burning shell or carry processed ashes out of it. These mixing processes are among the most uncertain and consequentially important aspects of massive stellar evolution. The amount of overshooting assumed in a stellar evolution model can change the predicted lifetime of the star, the mass of its core, the composition of its envelope, and its ultimate fate as a supernova. And there is no universally agreed upon prescription for how much overshooting to include. This uncertainty propagates through every subsequent calculation, contributing to the persistent difficulty of predicting the detailed behavior of stars like Enceladus. Then the helium is exhausted, the core contracts again, heating to roughly 600 million Kelvin, and carbon ignites. Carbon burning produces neon and magnesium, and it lasts approximately 600 years. Each successive stage is not only shorter but also more violent. The energy generation rates increase enormously. The temperatures climb to levels that begin to produce copious neutrino emission, and these neutrinos, unlike photons, pass straight through the overlying stellar material without being absorbed, carrying energy away from the core at an ever-increasing rate. From carbon burning onward, the star loses more energy through neutrino emission than through photon radiation from its surface. The star is literally bleeding energy through its core in a form that cannot be stopped or redirected, accelerating its consumption of fuel and hastening its approach to the final collapse. Then the carbon is gone, and the core contracts once more, reaching roughly 1.2 billion Kelvin. Neon burns next, lasting approximately 1 year. Then oxygen, at roughly 2 billion Kelvin, lasting about 6 months. And then finally, silicon burns. This is the last stage, the penultimate act. Silicon burning is different from all the preceding stages in a subtle but crucial way. The silicon nuclei are so massive and so highly charged that they cannot fuse directly with each other at any achievable temperature. Instead, silicon burning proceeds through a process called photodisintegration, in which the intense gamma-ray radiation field at the core's temperature, roughly 3 billion Kelvin, breaks apart some of the silicon nuclei into smaller fragments, alpha particles, protons, and neutrons. These fragments are then captured by other silicon and intermediate mass nuclei in a rapid series of reactions that gradually build up the nuclear mass number toward the iron group, the cluster of elements around iron, cobalt, and nickel that have the highest binding energy per nucleon of any nuclei in nature. Silicon burning lasts approximately 1 day, 24 hours, one rotation of the Earth on its axis. A star that spent 7 million years calmly fusing hydrogen will, in its last day of nuclear life, convert its core to iron in a frantic, desperate burst of nuclear activity. The acceleration is breathtaking. 7 million years, then 700,000 years, then 600 years, then 1 year, then 6 months, then 1 day. Each stage shorter than the last, by factors of tens and hundreds and thousands, as the star races toward its end with gathering, unstoppable momentum. Let that sink in. And once that iron core has formed, there is no more fuel. Iron is the endpoint of nuclear fusion as an energy source. It sits at the peak of the binding energy curve, the summit of nuclear stability. Fusing iron into heavier elements does not release energy. It absorbs energy. There is no nuclear reaction that can save the star from what comes next. The core, now a ball of iron roughly the mass of our Sun, compressed into a sphere the size of the Earth, has no source of energy to support itself against the crushing inward pull of gravity. The electrons, that have been providing some of the support, are squeezed into the protons, converting them to neutrons through inverse beta decay, and producing a flood of neutrinos. The core becomes a ball of neutrons and collapses. The collapse is catastrophic. The core falls inward upon itself at speeds approaching 1/4 of the speed of light. In less than 1 second, the core goes from the size of the Earth to the size of a city, roughly 20 kilometers in diameter. The density at the center reaches approximately 230 million metric tons per cubic centimeter. A teaspoon of this material would weigh as much as a mountain. The temperature soars to over 100 billion Kelvin, hotter than anything in the universe since the first fraction of a second after the Big Bang. Then the collapse halts. The nuclear strong force, the same force that holds protons and neutrons together inside atomic nuclei, provides a sudden, fierce resistance as the neutrons are squeezed to the point where they overlap. The material stiffens dramatically. The infalling outer layers of the star, still raining inward at tens of thousands of kilometers per second, slam into this incredibly dense, suddenly rigid core and bounce outward in a colossal shockwave. Neutrinos, ghostly particles that interact almost not at all with ordinary matter, pour out of the collapsing core in unimaginable numbers, roughly 10 to the 58 neutrinos in a burst lasting about 10 seconds. These neutrinos carry away roughly 99% of the total gravitational energy released, approximately 3 times 10 to the 46 joules of energy, in the form of particles that pass through the Earth as though it were made of glass. The remaining 1% of the energy powers the visible explosion, and even that 1% is enough to briefly outshine an entire galaxy of hundreds of billions of stars. This is a core collapse supernova. This is how the most massive stars die. This is not science fiction. This is not speculation. This is textbook astrophysics, supported by decades of theoretical modeling, numerical simulation, and direct observation. We have observed thousands of supernovae in other galaxies. We have detected the neutrinos from one, supernova 1987A, which occurred on February 23, 1987, in the Large Magellanic Cloud, the same galaxy that hosts Enceladus. The Kamiokande 2 detector in Japan and the IMB detector in the United States recorded a total of 24 neutrinos from this event, arriving in a burst roughly 13 seconds long. 24 particles, out of the roughly 10 to the 58 that were emitted. That is how weakly neutrinos interact with matter, and yet those 24 detections were sufficient to confirm the basic theoretical picture of core collapse, and to earn Masatoshi Koshiba a share of the 2002 Nobel Prize in Physics. The detection of neutrinos from SN 1987A was one of the landmark achievements of 20th century science, a moment when two previously separate branches of physics, particle physics and astrophysics, converged on the same event and confirmed each other's predictions. The theorists had calculated how many neutrinos a collapsing stellar core should produce, what their energies should be, and how long the burst should last. The experimentalists, using detectors originally built to search for proton decay, recorded an event that matched those predictions with remarkable fidelity. It was a textbook example of how science works at its best, a theoretical prediction made decades in advance, confirmed by observation, in a way that left almost no room for alternative explanations. The supernova mechanism itself, the process by which the collapsing core manages to reverse the infall of the star's outer layers and drive them outward in an explosion, has been one of the most challenging problems in computational astrophysics. For decades, the simplest models, in which the bounce shock from core collapse directly drives the explosion, failed. The shock wave, initially powerful, loses energy as it moves outward through the still infalling outer core. It expends energy photodissociating ion nuclei back into individual protons and neutrons, an endothermic process that drains the shock's kinetic energy. In one-dimensional simulations, the shock invariably stalls, losing its momentum at a radius of roughly 100 to 200 kilometers, and the star fails to explode. This was called the stalled shock problem, and it haunted supernova theory for years. The resolution, or at least the most widely accepted partial resolution, came from recognizing the role of neutrinos in reviving the stalled shock. The proto-neutron star at the center of the collapse continues to emit vast quantities of neutrinos, and even though neutrinos interact very weakly with matter, the densities in the region just behind the stalled shock are high enough that a small fraction of the neutrino energy is absorbed. This neutrino heating deposits energy into the material behind the shock, building up pressure, and eventually, in multi-dimensional simulations, that allow for convective overturn and the standing accretion shock instability, reviving the shock and driving a successful explosion. The details of this neutrino-driven mechanism are still being refined, and some of the most massive stars may require additional energy sources, such as magneto-hydrodynamic jets, driven by a rapidly rotating, strongly magnetized proto-neutron star, to produce the observed explosion energies. But the broad outline is now reasonably well established, at least for stars in the mass range of roughly 8 to perhaps 30 solar masses. For the most massive stars, those above perhaps 30 to 40 solar masses, the situation is less clear. Some theoretical models suggest that the most massive stars may fail to explode entirely, with the collapsing core swallowing the stalled shock and the entire star falling into a black hole in a phenomenon sometimes called a failed supernova or a direct collapse. Observational support for this scenario came from a program led by Christopher Kochenek at Ohio State University, which has been monitoring millions of stars in nearby galaxies, watching for cases where a massive star simply vanishes without producing a bright supernova. At least one convincing candidate has been identified: a red supergiant in the galaxy NGC 6946 that faded from view between 2009 and 2015 without producing the expected supernova luminosity. Whether S. Doradus is massive enough to face this fate, or whether it will have shed enough mass by the time of core collapse to produce a conventional supernova, remains an open and actively debated question. SN 1987A has a special relevance to the story of S. Doradus. It occurred in the same galaxy. Its progenitor star, later identified as Sandulac-69202, was a blue supergiant of roughly 20 solar masses. Before exploding, this progenitor star had shed a significant amount of mass through stellar winds, creating a complex circumstellar environment that shaped the appearance of the expanding supernova remnant. The now iconic ring structures surrounding the supernova remnant, visible in Hubble Space Telescope images, are understood to be material that the progenitor shed during an earlier evolutionary phase, possibly an LBV phase or a red supergiant phase, illuminated and heated by the ultraviolet flash of the explosion. The proximity of this supernova to S. Doradus in the Large Magellanic Cloud, while coincidental in position, is a poignant reminder that these processes are happening in the same galactic neighborhood, involving stars born from the same clouds of gas, sharing the same metallicity and the same cosmic environment. But S. Doradus is not waiting for its supernova to contribute heavy elements to the cosmos. It is doing it right now. Every eruption, every episode of enhanced mass loss, every dense wind that streams away from its bloated atmosphere, carries with it the products of nuclear burning from the star's interior. Spectroscopic observations of the material ejected by S. Doradus and other LBVs consistently show enhanced abundances of nitrogen, often by factors of 5 to 10 or more, compared to the composition of the surrounding interstellar medium. This nitrogen enrichment is a telltale signature of the CNO cycle at work. In the CNO cycle, carbon, nitrogen, and oxygen atoms serve as catalysts, shuttling protons from the hydrogen fuel to the helium ash. As the cycle operates, the relative abundances of these three elements shift. Carbon and oxygen are gradually converted into nitrogen through a series of proton captures and beta decays, until the system reaches an equilibrium in which nitrogen is dramatically enhanced relative to its initial abundance. The equilibrium favors nitrogen because one of the steps in the cycle, the reaction in which nitrogen-14 captures a proton to produce oxygen-15, is the slowest step, the bottleneck of the cycle. Material piles up at this bottleneck, like cars backing up behind a slow section of highway, producing a large excess of nitrogen-14 relative to carbon-12 and oxygen-16. When this CNO process material is dredged up from the stellar interior by convection or rotational mixing, and then ejected into space by stellar winds or eruptions, it carries its distinctive chemical signature with it. The nitrogen that S. Doradus is pumping into the Large Magellanic Cloud right now is overwhelmingly nitrogen-14, produced deep in the star's hydrogen-burning shell, transported outward by mixing processes that are not yet fully understood, and launched into interstellar space by the star's radiation-driven wind. Nitrogen is the seventh element on the periodic table, with 7 protons and typically 7 neutrons in its nucleus. It is essential for life as we know it, central to the structure and function of every living organism on Earth. It is a key component of amino acids, the building blocks of proteins, without which no enzyme could catalyze a biochemical reaction, no muscle could contract, no antibody could recognize an invader. It is a central atom in the nucleotide bases of DNA and RNA, the molecules that carry genetic information from one generation to the next and translate that information into the molecular machinery of living cells. It forms the backbone of many vitamins and cofactors essential for metabolism, and it is a major constituent of Earth's atmosphere, making up roughly 78% of the air you breathe, existing as molecular nitrogen, N2, a diatomic molecule so stable that it took billions of years for biological evolution to produce organisms capable of breaking its powerful triple bond and converting atmospheric nitrogen into biologically usable forms. Much of the nitrogen in the universe was produced in stars like Doradus through exactly the CNO cycle process that is happening right now, in real time, 160,000 light-years away. The total mass of material that Doradus will eject during its LBV phase is difficult to estimate precisely, but it is likely to be substantial. If the star loses mass at an average rate of roughly 10 to the negative 5 solar masses per year, which is a conservative estimate for a luminous blue variable, and the LBV phase lasts somewhere between 25,000 and 40,000 years, then the total mass lost during this phase alone would be approximately 0.25 to 0.4 solar masses. But this estimate is almost certainly too low because it assumes a constant mass loss rate and ignores the episodic giant eruptions that can dramatically increase the total mass budget. During a giant eruption, the mass loss rate can spike to 10 to the negative 2 or even 10 to the negative 1 solar masses per year, and a single event could eject several solar masses of material in just a few years or decades. Eta Carinae ejected roughly 15 to 20 solar masses during its great eruption in the 1840s, a staggering amount equivalent to more than 5,000 times the mass of the Earth expelled in roughly 2 decades. Over the full course of its post-main sequence evolution, including the LBV phase, any subsequent Wolf-Rayet phase, and the terminal supernova explosion, Doradus could return the great majority of its initial mass to the interstellar medium. A star that was born with perhaps 60 to 80 solar masses may retain only a few solar masses as a compact remnant, a neutron star, or a black hole, at the very end. Everything else, 50 to 70 solar masses of material enriched with the products of nuclear burning, is given back to the cosmos. This ejected material does not simply disperse uniformly into the void. It forms structures. The dense shells and clumps expelled during eruptions create a complex circumstellar nebula around Doradus, a layered record of the star's eruptive history written in gas and dust. Fast winds from the hot quiescent phases, moving at 1,000 to 3,000 kilometers per second, collide with slow, dense winds from the cool, eruptive phases, moving at only 100 to 300 kilometers per second. These collisions create shock fronts where the gas is compressed to high densities, heated to temperatures of millions of Kelvin, and made to glow in X-rays and ultraviolet light. The interactions between successive wind episodes sculpt the nebula into arcs, filaments, shells, and bipolar lobes that can be mapped using narrowband imaging, long-slit spectroscopy, and integral field spectroscopy. Each feature in the nebula corresponds to a specific mass ejection event, frozen in the expanding flow like a ring in a tree trunk, telling the story of the star's past eruptions to anyone with the instruments and the patience to read it. The most spectacular example of such a nebula is the homunculus surrounding Eta Carinae, a bipolar structure roughly 1/3 of a light-year across, expanding at over 600 kilometers per second, containing an estimated 15 to 20 solar masses of gas and dust. The homunculus is a direct, visible consequence of the great eruption of the 1840s, and its detailed structure, its asymmetries, its chemical composition, its dust content, its ionization state, provides an invaluable laboratory for studying the physics of massive stellar eruptions at close range. S. Doradus has its own circumstellar nebula, less dramatic than the homunculus, but no less scientifically valuable, a more modest structure that reflects its less extreme eruptive history during the period we have observed it. These circumstellar nebulae are not isolated curiosities. They are active participants in the ecology of their host galaxies. The mechanical energy injected into the interstellar medium by LBV winds and eruptions, combined with the ultraviolet radiation that the star emits during its hot, quiescent phases, creates a bubble of hot, low-density gas around the star, pushing against the surrounding medium and compressing it into a shell. This process, called stellar feedback, is one of the primary mechanisms by which massive stars regulate the star formation process in their host galaxies. The compressed shells of gas swept up by massive stellar winds and supernovae can become gravitationally unstable and collapse to form new stars, triggering a chain reaction of star formation that propagates through the interstellar medium. Alternatively, the energy injected by massive stars can heat and disperse the surrounding gas, suppressing star formation in the immediate vicinity. The net effect depends on the balance between these competing processes, a balance that is set by the number and distribution of massive stars, their luminosities, their wind properties, and the density and structure of the surrounding medium. In the Large Magellanic Cloud, which is actively forming stars at a vigorous rate, the cumulative feedback from massive stars, including S. Doradus and its neighbours, has shaped the structure of the interstellar medium on scales of hundreds of light years. The giant star-forming region, known as 30 Doradus, or the Tarantula Nebula, located in the same galaxy as S. Doradus, is one of the most intense concentrations of massive star formation in the entire local group of galaxies. It is powered by hundreds of O-type and Wolf-Rayet stars, many of which will pass through an LBV phase similar to S. Doradus before reaching their endpoints. The collective output of these stars, their radiation, their winds, their eruptions, and eventually their supernovae, drives the chemical and dynamical evolution of the Large Magellanic Cloud as a whole, shaping its structure, enriching its composition, and setting the stage for future generations of stars and planets. Zooming out further, the material that S. Doradus ejects will eventually merge with the general interstellar medium of the Large Magellanic Cloud. There, it will mix with gas from other sources, with the winds of other massive stars, with the expanding remnants of ancient supernovae, with the shells carved by clusters of hot young stars, with the pristine hydrogen and helium that continues to accrete onto the LMC from intergalactic space and from the cosmic web of filaments that feeds all galaxies. This enriched, well-mixed medium is the raw material from which new stars and planetary systems will form. And in those new systems, the atoms that were once part of S. Doradus will participate in new chemistry, new geology, new atmospheric processes, and perhaps, given enough time and the right conditions, new biology. The chain of causation stretches across billions of years. Hydrogen created in the Big Bang collapses into the first generation of stars. Those first stars burn, fuse heavy elements for the first time, and explode, seeding the interstellar medium with a thin dusting of metals. New stars, formed from this modestly enriched medium, burn more efficiently because the metals in their composition enable stronger opacities and more effective radiative driving, fuse even heavier elements, and explode in turn, adding their contribution to the growing chemical inventory. Each generation adds more complexity. Each generation produces stars that are slightly different from their predecessors because the starting composition has changed. This is galactic chemical evolution, the slow, generational enrichment of galaxies, from the primordial hydrogen-helium mixture of the Big Bang to the diverse elemental palette that we observe today. And eventually, on at least one planet, around at least one ordinary star in a relatively metal-rich region of a spiral galaxy, the accumulated products of roughly 9 billion years of stellar nucleosynthesis and galactic chemical evolution arrange themselves into patterns complex enough to become aware of their own existence. We are those patterns. We are the universe's way of knowing itself. And stars like S. Doradus are among the most important contributors to the chemical complexity that makes our existence possible. The star that seems most alien, most extreme, most removed from the gentle familiarity of our own sun, is in fact one of the most intimate contributors to the atoms in your body. The very violence that makes Enceladus so terrifying is the same violence that makes the periodic table so rich. The eruptions that shatter the star's atmosphere are the same eruptions that scatter nitrogen and carbon and oxygen into interstellar space. The instability that makes Enceladus impossible to predict is the same instability that, over cosmic timescales, makes planets and life possible. Destruction and creation are not opposites in this context. They are two aspects of the same process, inseparable, interdependent, woven together at every scale from the nuclear reactions in the star's core to the grand arc of cosmic evolution. There is one more dimension to this deeper truth that deserves careful attention because it concerns elements even rarer and more extreme than the carbon and nitrogen and oxygen that Enceladus is currently producing. The death of a star like Enceladus does not merely scatter existing heavy elements into space. It creates new ones, elements that cannot be produced under any other conditions in the universe. During the supernova explosion itself, the intense flux of free neutrons released by the collapsing core drives a process called rapid neutron capture, or the R process. In this process, seed nuclei, typically ion group elements already present in the star, are bombarded with neutrons at such an extraordinary rate that they absorb dozens of neutrons before the resulting unstable nuclei have time to undergo beta decay. The nuclei climb rapidly up the neutron-rich side of the chart of nuclides, reaching extremely neutron-heavy isotopes that are far from the valley of stability. When the neutron flux subsides, these bloated neutron-rich nuclei undergo a cascade of beta decays, converting excess neutrons into protons and moving the nuclei towards stability along chains that terminate at the stable isotopes of extremely heavy elements: gold, platinum, iridium, osmium, lead, bismuth, thorium, uranium, and many others. The R process requires conditions so extreme, temperatures exceeding 10 billion Kelvin and neutron densities exceeding 10 to the 20th per cubic centimeter, that they can only be achieved in two known astrophysical settings: the cores of collapsing massive stars during supernovae and the mergers of neutron-star binaries. Current research suggests that neutron-star mergers may be the dominant source of R process elements in the universe, following the landmark detection of gravitational waves and electromagnetic radiation from the neutron-star merger event GW170817 in August 2017, which provided strong evidence of R process nucleosynthesis in the merger ejecta. But core collapse supernovae, including the future supernova of Enceladus, also contribute, particularly for the lighter R process elements up to and including silver and palladium, the gold in a wedding ring, the platinum in a catalytic converter, the uranium that powers nuclear reactors and was forged into weapons that have shaped the geopolitics of the past 8 decades. These elements owe their existence, at least in part, to the deaths of stars like Enceladus, stars that burned too brightly, that pushed too hard against the limits of physics, that tore themselves apart in the process of forging the raw materials of future worlds. What does the existence of Enceladus mean for us? For the human species, perched on a small rocky world orbiting an average star in a suburban arm of an ordinary spiral galaxy, it means several things, and none of them are simple. First, it means that the universe is more violent than it appears from our comfortable vantage point. We look up at the night sky and see stillness, points of light, unchanging to the naked eye, arrayed in patterns that have remained recognizable for thousands of years. The constellations that Homer described are the same constellations we see tonight. The sky seems eternal, permanent, frozen in place. But this is an illusion of timescale. The sky is not frozen. It is seething with activity on timescales, both shorter and longer than a human life. Stars are being born in the dark interiors of molecular clouds, collapsing from tenuous gas into incandescent spheres of plasma in a process that takes a few 100,000 years. Stars are dying, some gently shedding their outer layers to form glowing planetary nebulae, others detonating in supernovae that briefly outshine their host galaxies. Nebulae are expanding and collapsing. Pulsars are spinning hundreds of times per second, sweeping beams of radiation across the cosmos like cosmic lighthouses. Black holes are swallowing matter and launching relativistic jets that stretch across millions of light years. Entire galaxies are colliding and merging, tearing each other apart with gravitational tides that rearrange hundreds of billions of stars over hundreds of millions of years. And individual stars like Enceladus, are breathing, pulsing, erupting, shedding their outer layers in slow-motion explosions that unfold over years and decades, timescales too long for a casual observer to notice between one night and the next, but too short to be captured in any single human lifetime of systematic observation. We live in a dynamic universe, a universe of process, not permanence, a universe where the very atoms that compose your body were forged in the hearts of stars that no longer exist, scattered by explosions that happened billions of years before the Earth was formed, gathered by gravity into a new solar system, accreted onto a rocky planet, cycled through oceans and atmospheres and living organisms for billions of years, and now, temporarily, impossibly, arranged into a configuration that can read these words and think about what they mean. The stability we perceive is real but local and temporary. On the cosmic scale, everything is in motion, everything is changing, everything is part of a vast, slow, ongoing transformation that has no discernible endpoint. Second, Enceladus reminds us of the concept of limits, a concept that applies far beyond the domain of stellar physics. Every physical system has a boundary beyond which it cannot sustain itself. The Eddington luminosity is one such boundary for stars, the point where radiation pressure overcomes gravitational binding and the star begins to come apart. But the concept applies with remarkable universality across many domains of physics and beyond. There is a limit to the mass of a white dwarf, the Chandrasekhar limit of roughly 1.4 solar masses, beyond which the electron degeneracy pressure that supports the white dwarf against collapse is overwhelmed, and the white dwarf either explodes as a type Ia supernova or collapses to a neutron star. There is a limit to the mass of a neutron star, the Tolman-Oppenheimer-Volkoff limit, roughly 2 to 2.5 solar masses, beyond which even the nuclear forces cannot prevent collapse to a black hole. There is a limit to the spin rate of a pulsar, set by the point where centrifugal force at the equator exceeds gravitational binding. There is a limit to the speed of information transfer, set by the speed of light. There is a limit to the precision with which certain pairs of physical quantities can be simultaneously known, as expressed by Heisenberg's uncertainty principle. And there may be limits to the complexity of systems, biological, technological, ecological, or social, beyond which stability gives way to instability, order gives way to chaos, and growth gives way to collapse or reorganization. Enceladus is a star that has reached its limit. It exists at the boundary of what a cell-luminous gaseous body can be, and at that boundary it is breaking apart, slowly, violently, beautifully. The physics is specific to stars, but the pattern is universal. Boundaries are where the most consequential events in nature tend to occur. Phase transitions, where water becomes ice or steam. Critical points, where the distinction between liquid and gas vanishes entirely. Bifurcation points in nonlinear dynamics, where a system that has been following one stable trajectory suddenly splits into two or more possible futures. Tipping points in climate systems, where gradual forcing produces abrupt, irreversible change. Enceladus exists at a stellar bifurcation point. Its future could lead to a Wolf-Rayet star, a luminous blue supergiant supernova, a neutron star, a black hole, a magnetar, or some combination of these outcomes. Which path it takes depends on the detailed interplay of mass loss, core evolution, angular momentum transport, and magnetic field dynamics that we cannot currently predict with confidence. The star sits at a fork in the road, and we do not yet know which fork it will take. Third, and perhaps most important for our sense of ourselves, the story of Enceladus underscores the profound interconnectedness of all things in the cosmos. We are not separate from the universe. We are not observers peering at an external landscape through a window. We are participants in the same physical processes that govern Enceladus, the same gravity that pulls the star's atmosphere inward and drives the contraction of its core, holds you to the surface of the Earth and keeps the Moon in orbit. The same electromagnetic force that governs the interactions between photons and electrons in the star's atmosphere governs the chemical bonds in your body and the electrical impulses in your neurons. The same nuclear physics that powers Asteroid's core powered every nuclear reactor ever built on Earth and is the source, ultimately, of every element heavier than lithium in your body. The same thermodynamics that drives convection in the star's envelope drives the weather systems of Earth's atmosphere, the circulation of its oceans, and the metabolic processes in your cells. You are a downstream consequence of stellar evolution, a late-stage product of the same nucleosynthesis that is happening inside Asteroidus right now. There is no separating line between astronomy and biology, no sharp boundary between the physics of stars and the physics of life. There is only physics, operating at different scales, under different conditions, producing different outcomes, but always the same fundamental laws, always the same particles and forces, always the same universe. There is a philosophical weight to this realization that grows heavier the longer you sit with it. Consider the carbon atom currently residing in one of the neurons in your brain, the neuron that is, at this very moment, processing the meaning of these words. That carbon atom was almost certainly not created in our sun. Our sun does not fuse carbon in its core. It is not massive enough to have reached that burning stage, and will not reach it for another 5 billion years. That carbon atom was created inside another star, a star that lived and died billions of years before our solar system was born. That star may have been a luminous blue variable, a star much like S. Doradus, that shed its outer layers in a series of violent eruptions, scattering carbon-rich material across light years of interstellar space. Or it may have been a lower-mass star that ejected its carbon during the asymptotic giant branch phase of its evolution, producing a planetary nebula. Or it may have been created in a supernova and scattered in the explosion. Regardless of the specific source, the trajectory of that atom is a journey that spans billions of years and billions of kilometers. That carbon drifted through the interstellar medium for millions of years after its creation, buffeted by stellar winds, heated by passing shock waves, cooled by radiative emission, occasionally combining with other atoms to form simple molecules, carbon monoxide, silicon carbide, polycyclic aromatic hydrocarbons, before being broken apart again by ultraviolet radiation or cosmic rays. It was swept up into the molecular cloud that collapsed to form our solar system 4.6 billion years ago, a cloud whose composition reflected the accumulated nucleosynthetic contributions of countless generations of stars. It was incorporated into the swirling disk of gas and dust that surrounded the young sun. It stuck to other grains and molecules in the disk, gradually accumulating into larger and larger aggregates through collisions and gravitational attraction. It accreted into a planetesimal, then into a protoplanet, then into the Earth. It was subducted into the mantle and released through volcanic eruptions. It was dissolved in ocean water and precipitated into carbonate minerals. It was taken up by photosynthetic organisms and incorporated into organic molecules. It passed through food chains, was breathed out as carbon dioxide, was absorbed by plants, was eaten by animals, was decomposed by bacteria, was recycled and rebuilt countless times, shuffled through molecule after molecule, organism after organism, ecosystem after ecosystem. And now, today, after a journey of billions of years from the nuclear furnace of a dying Xandar star to the synaptic cleft of a neuron in a primate brain, it sits in your skull, participating in the electrochemical processes that constitute your conscious experience. Let that sink in. You are thinking with atoms that were made in a star that may have looked very much like S. Doradus, a star that burned with the light of 1,000,000 suns and died in an explosion that briefly outshone its galaxy. That star is gone. Its light has faded. Its matter has been dispersed and recycled. But its legacy persists in the chemical richness of the interstellar medium, in the diversity of elements available to form planets and life, and ultimately in you. You are one of the things that stars' death made possible. There is a dimension to this interconnectedness that is often overlooked, and it involves not just the atoms themselves, but the dust. When Enceladus ejects material into the surrounding space, that material does not remain as bare, isolated atoms drifting individually through the void. As the ejected gas expands and cools, the atoms begin to combine. Carbon atoms find oxygen atoms and form carbon monoxide molecules. Silicon atoms find oxygen atoms and form silicate grains, tiny crystals of rock, barely a micron across, condensing in the expanding flow like frost forming on a window pane. Iron atoms cluster into metallic nanoparticles. Carbon atoms, where the carbon abundance exceeds the oxygen abundance, form soot-like grains of amorphous carbon. These microscopic particles of dust, invisible to the naked eye, but detectable through their infrared emission and their ability to dim and redden starlight passing through them, are among the most important products of massive stellar evolution. Dust is far more significant than its humble name suggests. In the interstellar medium, dust grains serve as surfaces upon which chemical reactions can occur, reactions that would be virtually impossible in the gas phase, because the reacting atoms would never find each other in the vast emptiness between the stars. Molecular hydrogen, the most abundant molecule in the universe and the raw material for star formation, forms primarily on the surfaces of dust grains. More complex molecules, including water, methanol, formaldehyde, and even amino acid precursors, have been detected in regions of the interstellar medium, where dust grains provide the catalytic surfaces needed for their assembly. Without dust, the chemistry of the interstellar medium would be radically impoverished, and the formation of molecular clouds, the dense, cold nurseries where new stars and planets are born, would proceed very differently, if it could proceed at all. Dust also plays a crucial role in the planet formation process itself. In the protoplanetary disk surrounding a young star, dust grains collide and stick together, gradually building up larger and larger aggregates, from micron-sized particles to millimeter-sized pebbles to kilometer-sized planetesimals, in a process that eventually produces full-sized rocky planets. The dust that forms in the ejecta of massive stars like Enceladus is one of the primary sources of the interstellar dust reservoir from which these protoplanetary disks are assembled. In a very real sense, the dust that Enceladus is producing right now, in its wind and in its eruptions, is the raw material for future Earths, future Marses, future rocky worlds that may one day harbour oceans and atmospheres and perhaps life. The connection between Enceladus and the existence of planets is not metaphorical, it is mineralogical. Observations with infrared space telescopes, including the Spitzer Space Telescope and more recently the James Webb Space Telescope, have revealed the dust content of LBV nebulae in unprecedented detail. The circumstellar environments of massive stars are rich in dust, with compositions that reflect the nuclear processing of the underlying star. Silicate dust, carbon dust, iron dust, and more exotic species have been identified through their characteristic spectral features in the mid-infrared. The total mass of dust surrounding a single LBV can reach several solar masses, a substantial contribution to the interstellar dust budget of the host galaxy. In low metallicity environments, like the Large Magellanic Cloud, where other dust sources, such as asymptotic giant branch stars, are less productive due to the lower abundance of seed elements, LBVs and their supernova descendants may be particularly important dust factories, contributing a disproportionate share of the dust needed to sustain the chemical richness of the interstellar medium. There is a fourth implication of the Enceladus story, one that touches on our aspirations and limitations as a species. The study of Enceladus pushes the boundaries of human knowledge to their current limits and, in places, slightly beyond. It requires the most advanced telescopes on the ground and, in space, the most sophisticated spectroscopic and photometric techniques developed over centuries of incremental improvement, the most powerful supercomputers running the most complex simulations in computational physics, and the deepest understanding of nuclear physics, fluid dynamics, radiation transport, and general relativity that the human mind has been able to develop. And yet, despite all of this formidable intellectual and technological firepower, we still cannot fully explain Enceladus. We can describe its behavior in exquisite observational detail. We can measure its properties to impressive precision. We can identify the physical mechanisms that are likely responsible for its instability. But we cannot predict its future with confidence. We cannot say when it will erupt next, how violent the eruption will be, how much mass it will lose, or when it will finally reach the end of its luminous life. The star humbles us. It reminds us that the universe is not yet fully understood, that there are phenomena out there that exceed our current capacity to model and predict, that the frontier of knowledge is not a line behind us, but a horizon ahead of us, always receding, always beckoning, always promising that there is more to learn. This is not a cause for discouragement. It is a cause for wonder. It is a cause for renewed effort, for sustained investment in the telescopes and the training and the computational resources needed to push the frontier forward. The fact that the universe contains objects like Enceladus, objects that challenge our understanding and resist our models and surprise us with unexpected behavior, is what makes science an ongoing, vital, living enterprise, rather than a completed catalogue gathering dust on a shelf. Every unanswered question about Enceladus is an invitation to deeper inquiry. Every failed model is a clue about what the correct model must include that the failed one left out. Every unexpected observation is a gift from the cosmos, a piece of data that narrows the range of possible explanations and guides us, step by careful step, closer to the truth. We are a species that emerged from stardust and has learned to study the stars from which that dust came. We are the universe's attempt to understand itself, an attempt that is still very much in progress, still incomplete, still finding its way. And in Enceladus, the universe has given us one of its most compelling, most beautiful, and most challenging puzzles. The tools available for studying Enceladus have never been more powerful than they are today, and they continue to improve. The James Webb Space Telescope, launched in December 2021, and now operating at the second Lagrange point, roughly 1.5 million kilometers from Earth, offers infrared sensitivity and angular resolution that far exceed anything previously available. With JWST, astronomers can peer through the dust that shrouds portions of Enceladus's circumstellar nebula and map its structure in wavelengths that ground-based telescopes cannot efficiently observe. They can detect faint emission from molecules and dust species that trace the chemical composition and physical conditions of the ejected material. They can resolve fine-scale structures in the nebula that correspond to individual mass ejection events, reading the star's eruptive history with a precision that was impossible even a decade ago. The extremely large telescopes currently under construction, the European Extremely Large Telescope in Chile, with its 39-meter primary mirror, the 30-meter telescope planned for Hawaii, and the Giant Magellan Telescope, also in Chile, will push ground-based optical and infrared astronomy to even greater depths. With adaptive optics systems that compensate for atmospheric turbulence, these giant telescopes will achieve angular resolutions rivaling or exceeding those of space telescopes, combined with enormous light-collecting areas that enable spectroscopy of unprecedented sensitivity. For Enceladus, this means the ability to dissect the star's spectrum in finer detail, to track changes in its wind and atmospheric properties on shorter timescales, and to resolve the individual clumps and filaments in its circumstellar environment. Time domain surveys, both ground-based like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, and space-based like future missions proposed by NASA and ESA, will monitor Enceladus and thousands of other massive stars with a cadence and photometric precision that will capture transient events, small eruptions, wind instabilities, and precursor activity that might signal an approaching major eruption or the final collapse to supernova. The theoretical frontier is advancing as rapidly as the observational one. Three-dimensional radiation magnetohydrodynamic simulations of massive stellar envelopes, still in their relative infancy, are growing more sophisticated with each generation of supercomputer hardware. Within the coming decade or two, it may become possible to simulate the full three-dimensional structure of a star like Enceladus, from its nuclear burning core to its outermost wind, capturing the full range of instabilities, convective motions, magnetic field amplification, and mass ejection events in a single, self-consistent model. Such a simulation would represent a transformative advance in our understanding, replacing the patchwork of partial models that currently describe different aspects of LBV behavior with a unified, comprehensive picture of the whole star as a dynamical system. A star at the edge of possibility, a star that embodies the tension between creation and destruction, a star that, in its dying, will enrich the cosmos with the materials for future worlds. We do not yet know all of its secrets, but we are listening, we are watching, we are measuring, and we are slowly beginning to understand. So here we are, at the end of a journey that has taken us from the surface of the Earth to the interior of a star 160,000 light-years away. A star that defies easy description. A star that exists at the absolute limit of what physics permits a self-luminous body to be. A star that is, by any measure, one of the most extraordinary things in the known universe. Doradus burns with the light of more than 1 million suns. That is not metaphor, that is measurement. Instruments trained on the Large Magellanic Cloud. Instruments ranging from ground-based spectrographs, peering through the turbulent atmosphere of the Earth, to space telescopes orbiting high above it, have quantified its luminosity, tracked its variations over more than a century, analyzed the spectrum of its light across wavelengths from the ultraviolet to the infrared, and determined that this single star, this one seething, pulsating, erupting sphere of plasma, produces more radiant energy per second than 1 million ordinary stars combined. It is a beacon visible across intergalactic space, a point of light so powerful that it can be individually identified and studied among the 30 billion stars of its host galaxy. And it is dying, not in the slow, graceful decline that awaits our Sun, which has billions of years of steady, predictable burning ahead of it before it swells into a red giant and gently exhales its outer layers into a planetary nebula. Doradus is dying on an accelerated timeline, shedding its own substance into the void, stripping itself layer by layer, eruption by eruption, driven by the same luminosity that makes it so spectacular. Its light is simultaneously its glory and its doom. The radiation that makes Doradus visible from 160,000 light-years away is the same radiation that is tearing its atmosphere apart, blowing shells of processed gas into the surrounding space, sculpting a nebula from the star's own flesh and blood. The Eddington limit, that invisible boundary where light becomes too powerful for gravity to contain, is not just a number in a textbook for Doradus. It is a lived reality, a daily struggle, a chronic condition. It is the boundary that the star presses against every moment of its existence, the threshold that it approaches and sometimes crosses, the line between a star that holds together and a star that disperses into the cosmos. Doradus spends its life dancing along this edge, sometimes retreating into a hotter, more compact, more quiescent state, sometimes surging outward into a bloated, cool erupting state, never fully stable, never fully at rest, always in motion, always in transition, always negotiating the balance between gravity's inward pull and radiation's outward push. The luminous blue variable phase is brief by cosmic standards, perhaps 25,000 to 40,000 years. In the life of a galaxy, that is nothing. In the history of the universe, it is less than nothing. A single heartbeat in a life measured in billions of years. And yet it is during this brief, violent, unstable phase that some of the most consequential acts of stellar astrophysics occur. Mass is shed, hydrogen envelopes are stripped, the products of nuclear burning are scattered into the interstellar medium. The chemical composition of the galaxy is incrementally altered, enriched, complexified. The raw materials for future stars, future planets, future water, future organic chemistry, future life are delivered to the cosmos by a star that is too luminous to survive. There is an irony here that approaches poetry. The most generous stars in the universe are the ones that cannot hold themselves together. The stars that give the most to the cosmos are the ones that the cosmos breaks apart. We do not know exactly when Doradus will reach its end. We do not know whether it will transition to a Wolf-Rayet star, spending its final tens of thousands of years as a stripped, scorching, helium-burning core, its hydrogen envelope entirely gone, its surface a furnace of carbon and nitrogen and oxygen exposed to the vacuum of space before the final core collapse. We do not know whether it will explode in something resembling its current bloated state. producing a supernova whose blast wave will slam into the thick, multi-layered nebula of its own making, creating one of the most luminous and long-lasting transient events in the observable universe. We do not know whether it will leave behind a neutron star spinning madly in the wreckage, broadcasting radio pulses into the darkness, or a black hole swallowing the light that once streamed outward in such profusion, bending space and time around an infinitely dense point, visible only by its gravitational influence on surrounding matter. These are questions that time and continued observation and perhaps new theoretical insights may eventually answer. But for now, Enceladus keeps its final secret. What we do know is this: the atoms that Enceladus is forging and scattering right now, the nitrogen and carbon and oxygen and all the heavier elements that will be created in its eventual supernova, will outlast the star. They will drift through the Large Magellanic Cloud for millions of years, cooling, spreading, mixing with the ambient gas, losing all memory of the specific star that created them. They will be gathered into new molecular clouds by the slow, patient workings of gravity. They will collapse under their own weight into new stars and new planetary systems. Stars and planets whose compositions will be slightly different from anything that existed before, enriched by one more cycle of stellar nucleosynthesis, one step further along the endless chain of cosmic chemical evolution. And some of those atoms, perhaps, on some distant world, orbiting some future star that has not yet been born, will participate in something that we would recognize as life. Not our kind of life necessarily, not DNA and proteins and cells, but organized matter, complex chemistry, structures that persist and reproduce and adapt, patterns in matter and energy that are, briefly, impossibly, complex enough to wonder where they came from. And yet it is worth pausing to appreciate just how much we have learned about this star. Despite its distance, despite its complexity, despite all the obstacles that stand between a curious species on one small planet and a turbulent hypergiant in another galaxy. When the first astronomers in the southern hemisphere pointed their telescopes at the Large Magellanic Cloud in the 19th century, they could see that Enceladus was bright and that its brightness changed. That was all. They had no theory of stellar evolution, no understanding of nuclear fusion, no concept of the Eddington limit, no way to measure the star's temperature or composition or mass loss rate. They could only watch and record and wonder. In the 140 years since, successive generations of astronomers have built an understanding of Enceladus that would have astonished those early observers. We know its luminosity to within perhaps a factor of 2. We know its temperature varies between roughly 8,000 and 30,000 Kelvin, depending on its eruptive state. We know its mass loss rate and have tracked how it changes during eruptions. We have mapped its circumstellar nebula and identified the chemical signatures of CNO processing in its ejected material. We have placed it in the context of stellar evolution theory, understanding it as a transitional object between the main sequence O stars and the stripped envelope Wolf-Rayet stars. We have identified dozens of other stars in the Milky Way and other galaxies that share its properties, establishing the luminous blue variable class as a recognized stage in massive stellar evolution. We have connected its behavior to the fundamental physics of the Eddington limit and to the opacity properties of iron in stellar envelopes. And we have recognized, with increasing clarity and increasing humility, the profound importance of stars like Enceladus in shaping the chemical evolution of galaxies and the ultimate habitability of the universe. All of this from a point of light 160,000 light-years away. All of this from photons that left the star when Homo sapiens was a young species, when the ice ages had not yet carved the Great Lakes, when the Sahara was still green. The achievement is extraordinary, a testament to the power of patient observation, careful reasoning, and the cumulative, collaborative nature of scientific inquiry over multiple human lifetimes. The fabric of the cosmos is woven from the deaths of stars. This is not a metaphor. It is chemistry. It is physics. It is the observable, measurable, verified truth of how the universe became the complex, structured, element-rich place that we inhabit. Without stars like Enceladus, without their furious burning and their violent deaths, there would be no carbon, no oxygen, no silicon or iron or calcium, no rocky planets, no oceans, no atmospheres capable of supporting complex weather or photochemistry, no amino acids, no nucleotides, no lipid membranes, no life. The universe would still exist, but it would be a simpler, emptier place, an endless expanse of hydrogen and helium drifting in the dark, with nothing in it complex enough to ask why it was there. Somewhere in the Large Magellanic Cloud, 160,000 light-years from where you are right now, a star is burning itself alive. It is shedding its skin in slow, luminous eruptions that unfold over months and years. It is pressing against the very edge of the physically possible, generating more light than 1 million ordinary stars, pushing against the Eddington limit with every photon it produces. Its light left the star 160,000 years ago, when our ancestors were walking the savannas of Africa, when the ice ages were reshaping the continents, when the idea of a telescope, of a space observatory, of a theory of stellar evolution, of a YouTube video explaining it all, would have been utterly beyond imagining. That light has been travelling toward us ever since, crossing the intergalactic void at 300,000 kilometers per second, arriving at our instruments tonight as a quiet, steady signal from across the cosmos. One day, perhaps soon by cosmic standards, perhaps not for tens of thousands of years, that signal will change. The light will surge upward in a brilliant, unmistakable spike, or it will falter and fade. The core will fail. The iron will accumulate, atom by atom, fusion by fusion, until the mass of the iron core exceeds the Chandrasekhar limit, and the electrons that have been supporting it against gravity can no longer hold. The collapse will begin, and in less than a second, the star that took millions of years to build will be compressed into an object the size of a city. The shockwave will tear outward through the layered shells of nuclear burning, through the bloated, wind-sculpted atmosphere, through the circumstellar nebula carved by 100,000 years of eruptions, and into the interstellar medium of the Large Magellanic Cloud, carrying with it the products of every nuclear burning stage from hydrogen to silicon, plus the R process elements forged in the cataclysm itself, and the star called Estoradus, the star that gave its name to an entire class of cosmic variables, the star that outshone 1 million suns, will cease to exist as a star. But the atoms it made will endure, the elements it forged will persist. The nitrogen and oxygen, and carbon and iron and gold, and platinum and uranium it scattered, will drift and gather, and combine and build. Somewhere, someday, something new will arise from the remnants of Estoradus, something that we cannot predict, something that we cannot imagine, something that may, in its own way, be as improbable and as beautiful as the star that made it possible. Until that day, Estoradus burns, brighter than 1 million suns, trembling at the edge of its own destruction, pouring light into a darkness that stretches 160,000 light-years in every direction, a single astonishing, doomed point of radiance in the infinite night. And in that light, if you look carefully, you can read the story of everything that ever was, and everything that ever will be. If this video changed the way you think about stars, about atoms, about your own place in the cosmos, consider subscribing and sharing it with someone who might feel the same. The universe is telling its story, one star at a time, and some stories are too extraordinary not to share.